Well, for our last video on the topic of relations, we've got several definitions, a very trivial theorem that will show a very trivial proof, and then we've got a few examples, but mostly definitions. Okay, let's let this set A with this operator, relational operator, be a poset, a partially ordered set, and let B, capital B, be a subset of A. I put this in the definition simply to remind us what it means to be a poset. A poset has to be reflexive, anti-symmetric, and transitive. Part A and Part B, they're very, very similar, just a few words difference in each one of these definitions. For U, an element of A, if it's the case that B is less than or equal to U, for all B in the set B, then U is called an upper bound for B. If, let's see, for some element script L in A, if it's an upper bound, which we just defined, for B, and it is less than or equal to U for all other upper bounds U, meaning it's the smallest possible upper bound, then L is the least upper bound for B. And we'll write that L-U-B of capital B, least upper bound, the smallest of all of the upper bounds, the smallest one you could possibly get. Capital L is the maximum of B, a new term, and we'll write it like this, max of B, if it is the least upper bound and it's also in the set. It's only a maximum, it can only be a maximum if it is in the set. So the maximum is in the set and it's greater than or equal to all of the other elements. And the least upper bound doesn't have to be in the set, but it's greater than or equal to all of the elements. And there's no other number greater than or equal to all of them, yet smaller than, what did we call it? Script L, the least upper bound. All right, well, this is just analogous. Only instead of upper bounds, we're looking at lower bounds. For V, some number in A, if V is less than or equal to B for every B in the set, capital B, then V is a lower bound for B. For G, a member of the set A, if it is a lower bound for B, and it happens to be bigger than all of the other lower bounds for B, bigger than or equal, then it is the greatest lower bound that we call, for the set B, we'll call it GLB, greatest lower bound for B. M is the maximum of B, and it's written max of B, if it is the least upper bound and it happens to be in the set as well, in the set B. So very simple. If you have to take the set integers from 1 to 10, the number 50 is an upper bound. The number 20 is an upper bound. The number 11 is an upper bound. The number 9.5 is not an upper bound because 10 is greater than 9.5. The number 10 is an upper bound of the set 1 to 10. It's not only an upper bound, it's the least upper bound. And 1 would be the greatest lower bound of that set. Okay, that very simple theorem I mentioned. If A is a subset of the reals, and script L happens to be minimum of A, remember that means it's in the set, the minimum number in A, then it's unique. You can't have more than one minimum. And the proof is very simple. If M, look for a different one than L. If M is the minimum of A as well, then M is less than or equal to L because it's a minimum. But because L is a minimum, L is less than or equal to M. So we've seen this situation before. If M is less than or equal to L and L is less than or equal to M, that means M is equal to L. M is the same number as L, and L is unique. Simple proof. And the next one I'm leaving out that might be a homework problem for you, prove that the maximum of A is unique. It would literally be the statement of the theorem and the proof. Erase about 5 or 6 or 8 characters, replace mins with maxes, less thans with greater than or equals, and you'd have this proof done. Okay, an example. Let's let A be two real numbers where A is less than B. So on the left in the number line. Let I be the interval, closed interval from A to B, so it includes all of the numbers greater than or equal to A and less than or equal to B. And you could go through your notes and verify that it is a post set. Frequently, less than or equal is a nice operator to use for a post set. Well, notice that. Let's take this set right here. What is the least upper bound of I? Among all of the upper bounds, what is the smallest one there is? Well, it would be B. B is greater than every single element from A to B. Greater than or equal to that. And if you made it any smaller, it would not be an upper bound. And in this case, B is in that set. So that's also the max I. I believe that's always the case. If you have the least upper bound and it is in the set, then we call it the maximum. You can call it both, either way. Okay, now let's change one thing. Let's use I prime and make it an open interval. Oh, I'm sorry, I guess I didn't finish this. Let's use least upper bound, greatest lower bound of I. The greatest lower bound is going to be A. And that also happens to be the min, the minimum of A. Now we're going to do the same thing with I prime, which is the open interval. Well, the least upper bound of I prime is still B. B is, now I can say B is greater, strictly greater than every element in this set, because B is not in this set, remember. But if I take any number smaller than B, it's going to put me inside the interval. And it would no longer be an upper bound. So that's the least upper bound, and there is no maximum value. So I will say max I prime does not exist. There's no element in this set that is greater than all the other ones. If you came up with one here, I would just go halfway to B, and I would have found a bigger one. And then I could go halfway again, and that process would never stop. So there's no maximum element. And then the greatest lower bound, greatest lower bound of I prime is going to be A again. And the min I prime does not exist. So greatest lower bound and a least upper bound will always exist, but a minimum and maximum will not always exist. And we just showed this example right here. Okay, definition and an example, and we'll be done. Definition. For this post set, let B be a subset of A. And I took M and M, little m and big M, because one of them is going to go minimal, one of them is going to be maximal. Numbers in B. If there is no B, little b, in the set B, with this one taken away, so we're ignoring this one, we don't want to use it again. So if there is no b in this set such that it's less than or equal to m, then we found a minimal element. That little m would be a minimal element. There is no other number different from m that's less than or equal to it. Likewise, if there's no b in b minus capital M, such that b is greater than or equal to m, I wrote it as m less than or equal to b, then capital M is a maximal element of b. So simple definition. And we're going to use this definition now in our last example. Consider a poset, partially ordered set A, where the set A is defined to be, remember this, script P is the power set of all of these elements, the set of all subsets. If you remember, there are 5 elements. So there are 2 to the 5th, which is 32 elements in the power set. From the empty set to the elements that contain, the sets that contain 1 element, the subsets with 2 elements, the subsets with 3 elements, the subsets with 4 elements, and then finally this set. If you add them all up, you get 32 of them. That was just a review. Okay, what's the ordering we're going to use? We're talking about sets, so we're not going to say less than or equal. A set is not less than or equal to another, but you can say a subset of each other. And we want to find the minimal elements and the maximal elements. So let's look at B first, the set capital B. It contains 4 sets. They're all subsets of 1, 2, 3, 4, 5. Let's look for a minimal element. And by the way, you think there could only be one minimal element? Seems like there should be, but no, it's not the case. We'll see right here. Okay, well, let's look at how the subsets go. This one is a subset of this one, which is a subset of this one. And that one's not a subset of anything. Is there anything that is a subset of this one in the set, other than itself? A set is always a subset of itself, but no, none of these sets is a subset of this, therefore it's minimal. 1, 2 is minimal. Go to the next one. Is there anything that's a subset of this? Yes, this one. It's not minimal. Anything that's a subset of this? Yes, this one and this one. This one is not minimal.